fixed bias configuration. It is the simplest biasing arrangement for the N-channel JFET. It is one of the few FET configurations that can be solved just as directly using either the mathematical approach or a graphical approach. Both methods are included in this lecture to demonstrate the difference between the two philosophies and also to establish the fact that the same solution can be obtained using either method. The configuration in the first figure includes the AC levels VI and VO and the coupling capacitors C1 and C2. Recall that the coupling capacitors are open circuits for the DC analysis. Okay. This magiging open ito. In the DC analysis of transistors, the C1 and C2 will become open. And the low impedances for the AC analysis, so for AC analysis, these capacitors will become short circuits. Okay? Capacitors in DC analysis will become open circuits, while capacitors in AC will become short circuits. So here the resistor RG is present to ensure that the input voltage appears at the input to the FET amplifier for the AC analysis, which will be discussed later. So for the DC analysis, IG is approximately equal to 0 amperes. So VRG here, the voltage across VRG, so VRG is equal to IGRG using Ohm's law. But then, substituting the value of IG, 0 amperes, this gives us a value of 0 volts also. So, in the DC analysis of the fixed bias configuration, RG was removed. Okay, it's no longer here in the circuit or in the network. So, this is the DC equivalent circuit of the fixed bias configuration given in the first figure. So, moving on. So, the 0 volt drop across RG permits replacing RG by a short circuit equivalent as appearing in the network. So, the fact that the negative terminal of the battery, okay, here, the negative terminal of the battery is connected directly to the defined positive terminal of the VGS. So the negative is connected to the positive terminal of the VGS clearly reveals that the polarity of the VGS is directly opposite to that of the VGG. So here, the negative is connected to the positive and the positive is connected to the negative here. So applying voltage, Kirchhoff's voltage law in the clockwise direction as indicated by the arrow. So the resulting equation is KVL we have negative VGG minus VGS is equal to 0, giving us VGS is equal to a negative VGG. So, since VGG is a fixed DC supply, so the voltage VGS is fixed in magnitude, resulting in the designation fixed bias configuration. You have here a fixed DC supply, this negative VGG. Okay. So the resulting level of the drain current ID is now controlled by the Shockley's equation. So I'll just put it here. The value of the VGS is equal to negative VGG. So next is for the value of the ID, and ID can be obtained using the Shockley's equation. ID is times the quantity 1 minus VGS all over the pinch of voltage squared. So since VGS is a fixed quantity for this configuration, okay, its magnitude and sign can simply be substituted into the Shockley's equation. So here, and the resulting level of the ID is calculated. So this is one of the few instances in which a mathematical solution to an FET configuration is quite direct. So that's it. So for the value of the VDS, okay, so the drain to source voltage of the output section here, so here the VDS, so we have the VDS here. So the VDS can be obtained by here applying Kirchhoff's voltage law again, beginning from the VDD going to that direction. So KVL so using KVL we have V VDD minus ID RD minus VDS is equal to 0. So giving us the value of VDS equal to VDD minus ID RD. So that's it. So for the other parameters, since VS, we have no voltage drop from the terminal, source terminal to ground, so we have VS is equal to 0 volts. And again, so using the double subscript notation, so we have to get the value of the VD here, going to ground, we have VD is equal to the value of VDS. Okay, here VD. And for the last one, for the value of gate voltage going to ground, so that is simply equal to the VG is simply equal to VGS. Okay. So this will be our formulas in dealing with the fixed bias configuration. Okay, so this will be the mathematical approach of the JFET, okay, of the first configuration, which is the fixed bias configuration of a JFET. And in here, this will be the graphical approach or method in dealing with the fixed bias configuration. So first, we will apply the mathematical approach in solving this problem. So we have to determine the following for the network: the VGSQ, the IDQ, the VDS, the VDVG, and the VS of the given network. So how do we get VGSQ? Okay, the solution. So we write here, so solution. So for our letter A, VGSQ. So how do we get our VGSQ? So from our notes a while ago, our VGS, since that is the quiescent value, so VGSQ is simply equal to the negative VGG of the network. So let's see here. Okay, where's the negative VGG? Here is our VGG of the given network. So VGSQ is simply equal to the negative VGG, equal to negative 2 volts. Next is how about the IDQ of the given network? So IDQ can be solved using the Shockley's equation. IDSS 1 minus VGS all over the pinch of voltage, the quantity square. So we substitute, since IDSS is given, so we substitute the given values is IDSS is 10 milliamperes. So we have here 1 minus the VGS. Okay, VGS is already computed, which is equal to negative 2 all over, okay, the pinch off is given with a value of negative 8 volts. So we have that, the quantity squared. So kindly compute for this. So our resulting IDQ is equal to a 5.625 milliamperes. So next is how about the value of the VDS. So VDS can be obtained with the value or with the equation VDD minus ID RD. Okay. VDD is given with a value 16 volts. ID, okay, we have already computed for the value of the ID, which is equal to 5.625 milliamperes. And RD is given with a value of 2 kilo ohms. So let's simplify our solution minus, so this is 11.25 volts. So we get our final value for the VDS equal to 4.75 volts. Okay. So next is how about the value of VD? So VD is from here to the ground. Okay, so from here to the ground. So what is the value of VD? So VD is just simply equal to the value of VDS. So they are the same. Okay. Also with a value of 4.75 volts. For VG, that is from the gate terminal to the ground. So we have what? Yes, it is the same as the value of the VGS. Okay, so we have here the value of the VGS. So VGS, which is equal to a negative 2 volts also. And for the last one, last unknown, we have the VS. So VS, okay, for a fixed bias configuration, okay, there's no resistor in between or being connected in the source terminal. So VS is simply equal to 0 volts. Okay, so that's it for the mathematical approach of this given circuit. So as we continue on the graphical approach of the fixed bias configuration, okay, we have here the graphical solution. So we have the different cases here, where case 1 we have the VGS, we set that to 0 volts, and so here, so this is the X, and so these are the corresponding points to the graph. Okay, so we set VGS to 0, and ID is equal to the IDSS. So our IDSS from the previous okay, with the same with our example is IDSS is equal to 10 milliamperes and VP is equal to negative 8 volts. So we have here 10 milliamperes. So this is the point for the case 1. And then maybe I will just use a different color. Okay. So let's take this green. So this is our point for the case 1. We have a 0 and 10. For the case 2, we set ID to 0, and then our VGS is equal to the V peak, which is equal to negative 8 volts. So here, so V peak equal to and then case 3, our VGS will be equal to VP over 2. So we have here negative, so somewhere here, and our IDSS is equal to 2.5. So here, so maybe that is our 2.5. So somewhere here. So somewhere here is our point for the case 3. That's negative 4 and a 2.5, and then for the last one we have a 0.3 of negative 8, so that gives us 2.4. So maybe here, okay, somewhere here midway, and then our ID is equal to IDSS over 2, which is 5. Okay, maybe somewhere here. Okay. So our transfer characteristic curve will most likely like this. Okay. Maybe I'll switch again to say this orange. So to draw the characteristic curve, so we have something like this. So this is our transfer characteristic curve. So our VGSQ, which is equal to a negative VGG, which is equal to negative 2 volts, will be somewhere in here. So if we draw a straight line, okay, we will draw a straight line upward the VGSQ here. Okay. So the intersection of this to the transfer characteristic curve will give us our Q point. So here. So the intersection here will give us our Q point. So this is our Q point here. So it has values negative 2, and that is in between the 5 and the 6. Okay, so maybe that is 5.6. Okay, so and this will be equal to our IDQ also. So our IDQ, our computed value for the IDQ is equal to, yes, that is 5.625. So since in the graphical approach, it's so hard to see beyond the beyond the second decimal place. So so we'll just estimate that to 5.6 milliamperes, which is almost which is very near value with our computed value, which is 5.625 in exact. Okay, so that's the graphical approach. And for the so again, our VGSQ is equal to the negative VGG, which is equal to negative 2 volts as shown here. So if we draw a line upward to that, and the intersection, the intersection of that line with the transfer characteristic curve, here, will give us the Q point of the transistor. And so the IDQ derived from the graph is equal to 5.6 milliamperes. And for the VDS, our VDS so our new VDS based from the value here, the 5.6 milliamperes will give us VDD minus the IDRD again. Our VDD is 16 volts minus a 5.6 milliamperes, and the value of our RD is 2 kilo ohms. So giving us a value of 4.8 volts, which is, if you compare to that with the computed value, that is equal to here, that is equal to 4.75 volts. So they are nearly the same. So our VD, again, that is equal to the VDS, 4.8 volts, and VG is equal to the VGS, which is equal to a negative 2 volts. And of course, Vs will still the same. That will be equal to the cos. So that's it for the fixed bias configuration of FET, both the mathematical approach and the graphical approach.